And we have to pass that negative through. All right, we all good? So look, we started out with this. We've done integration by parts twice. And now our new integral has what we're looking for again. Do y'all see it though? What do you see? Okay, so this side, we're saying the left side is this, integral sine x e to the x dx, right? And over here, they don't quite cancel. If they cancel, that'd be bad. If they cancel, then you would get basically something equals 0. And they don't cancel, but you can move this one to the other side because it's subtracted. So you can add this integral to this side of the equation, and you can add that integral to this side of the equation. And how do you add integrals? The same way you add apples. An apple plus an apple is 2 apples, right? So we have 2 integrals now, right? 2 integrals equals whatever's left over there. Okay, so let me write that down. 2 of these integrals equals whatever was left here. What was left? Sine x e to the x minus cosine x times e to the x, right? Where did what? Where did this come from? I'm adding on both sides, right? So 2 of these integrals is equal to that. What are we trying to solve for? This integral, right? So let's get rid of the 2 now. Divide. Divide by 2. Multiply both sides by 1/2. And we have somehow miraculously made it. The integral of sine x e to the x dx is just 1/2 sine x times e to the x minus 1/2 cosine x times e to the x. Now we do need to throw a constant of integration out here because every antiderivative must have a constant. Now that was weird, right? I mean, that was like the integral we were looking for appeared on the other side, like it appeared again, and then we were able to add it and everything just worked out beautiful. So good. All right, let me go to my notes because in my notes I have a couple of examples, okay? And I have not been doing those intentionally because, well, I get kind of tired of doing them. So I was just making those up as we go. But let's look at these and talk about these now. This first one right here, we did do, right? Okay. The second one, ooh, that one we haven't done. Okay, so let's skip the part B. How about this one right here? T squared cosine beta t. Where here beta is just like, that may as well say like 5t. It's a constant. How could you do this one? Let u be t squared. And you'll have to do integration by parts twice. First time through, it'll knock the t squared down to a t. Second time through, it'll knock the t down to just 1. Okay, how about this one? E to the 2x cosine x dx. That's like the one we just did. And I call it the rabbit out of the hat because it like all of a sudden appeared on the other side, right? So that's kind of like the trick we use for something like this. This one we've done, that one we've done. We haven't done part B, E, or F. So let's look at B, something like that one. Integral what's the antiderivative of arc sine of pi x? Now look everyone, I understand that we have a formula on our formula sheets that will tell us what the derivative of arc sine of x is, right? But we do not have a formula on our formula sheets that tells us what the antiderivative of arc sine is. Agree? All right. Luis. Yeah, unless there's something else, but I mean, yeah. Do you remember last class me saying that, like, the good news was that you kind of knew we were in the section on substitution, so the problems I was putting up here, you were doing substitution. But I said later on that's going to suck because you're going to have all these different things. Like, that's now what we're starting to get to. Like, here's a problem. You got to make sure you can't do it with substitution. It's not some basic formula off your sheet. So because today's integration by parts, yes, we're going to make a table. All right? So if we make a table, got to choose a u, got to choose a dv. Any thoughts about that?
I'll make the u the arc sign.
You have no other choice, right? The arc sine of pi x, that has to be u, right? Has to be. So while you're writing it down, you're asking yourself, you're saying, hey, can I take the derivative of that? Right? I'm going to need to, right? Can you? Yeah, okay. Now, if we do that for u, what's dv have to be then, Luis? What's the only thing left up in the integral that you haven't? The dx, which is like a 1 dx. So this is the first time we've ever had this, right? This is the first time we've ever just let our dv be dx. Every other time we've done it, it's been something else. Yes?
So it's legal to take the whole thing?
Well, we didn't take the whole thing. We took everything but dx. Okay? No, because sine inverse by itself doesn't have any meaning. You have to have sine inverse of something. So these are attached. There's no way to split those apart. Right? Yes?
Yeah.
Okay. All right, now let's complete the table. I'm going to move on because I wasn't sure how that would go. So let's see here. Erica. Where's Erica? Okay, Erica. Can you finish this table off?
Yes.
Okay.
So du is 1 over the square root of 1 minus pi x squared, or all that squared.
All that squared. Can I write pi squared x squared? That would be the same, right? That's the pi x being squared. One,
Oh, times pi.
good, times pi dx. Okay, so just using the chain rule on this, right? The formula for this, 1 over square root of 1 minus x squared, but for us the argument is this. So you square that, and then you have to take derivative of what's inside, which is pi. Perfect, everything, great. Okay, now, this way. V is x. That's it, x. Now, Erica, you're probably a little nauseous now looking at what the new integral is going to be, right? Is everyone slightly nauseous from what this is going to look like, this new integral? Voodoo, right? Voodoo is always the thing you're going to have to wind up dealing with at some point. But Luis picked this, right? And it wasn't a 50-50 thing. He had no choice but to do that, right? There was no other option. So we just have to proceed and see if this method is even going to work. So let's keep it going. Good with the table. Let's keep moving through people here. Gina? Gina? Okay, Gina, you're up. So I just want ultraviolet minus voodoo written out.
So sine, arc sine,
Mm-hmm. Times
x.
x. So I'm going to put the x in front. Okay, so x, arc sine of pi x,
Minus integral
minus a little bit of a space there in case we pull anything out.
x times
Yeah.
pi over
Yeah, x times, I'll write it down. X times pi over, whoa, I don't know what happened there. Square root of 1 minus pi squared x squared dx. My pi got a little bit stretched out there. Okay. Everyone agree?
Can I pull that pi out?
Yes, you can pull the pi out. Jace, you caught up as far as writing everything down at this? Okay.
By out of curiosity, can you just write that as pi x over?
Yes. Yes. That pi is pretty much at your disposal. You can leave it here, you can move it out front. All right, Jace. The whole idea behind this is that when you do integration by parts, you better be able to handle the new integral, right? Up to this point, we've been able to handle the new integral. So when you look at that integral, do you have any idea how to handle that?
Imagine like that, then on the set, pull up the pi.
Okay, okay, so let me get the pi out. Okay, there, it's gone. Put a 1 up here. Yes?
Can you do substitution now?
Sure. Everything's on the table. Why would you do substitution?
I was just curious if you could.
Oh, I thought you saw that there was a substitution that works. There is. So this is substitution now. Do you see something in its derivative?
Yeah, squared.
Okay, what do you see?
1 over the square root of 1 minus pi x squared is the antiderivative of sine.
Yeah, but you don't have a sign up there. We're going back to last class. You look in here, you say, do I see something and its derivative? The derivative can't be trapped. I can be off by a constant. U would have to be x squared, definitely, but how about we grab the whole thing? 1 minus pi squared x squared. Why don't we grab the whole radicand? The whole thing. Now, how would you know that this is the right thing to do here? Practice, 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 practice. And it's hard to absorb this material in such a short period of time. And that's what we've been trying to say about this class. It's difficult because it's a lot of information and it has to be absorbed quickly. If you've seen it before, if this is your second time through it, then it's a little easier. But first time through it, it's like there's no delay, there's no lag time. You don't get to go get caught up. It's like this now needs to be something that's built in now. I hope I'm making sense. And it's I'm the messenger, right? I've tried to say this. I'm the messenger. This is the way the class is. I can't undo that. Okay, so here's the substitution, right? Does everyone see why this substitution works now? What is the derivative of this? Negative 2 pi. 2 pi what? Negative 2 pi squared x. Remember, derivative of 1 is 0, right? This is negative pi squared is a constant, so we just ignore it. What's the derivative of x squared? 2x. So the 2 pops out, right? And then the negative and the pi squared is still there, and then we have dx. So the question was, do you see this? Do you see this somewhere in here? And you can be off by a constant. Do y'all see it? It's there, right? X dx, x dx. You're off by a bunch of stuff. You're off by that whole thing. Yes?
You said pi squared is just a constant.
That's right.
So the derivative of a constant is 0.
If it's by itself, like derivative of 1 was 0, right? But pi squared is attached to the x, right? It's attached through multiplication, so it comes for the ride. So here we've got 1 over, or I'll put negative 1 over 2 pi squared du equals x dx. So at this point, can't I rewrite this integral? I can rewrite this. But what I'm going to do is I'm going to do it over here because this is almost like scratch work that I'm doing now. What does the integral of x times 1 over the square root of 1 minus pi squared x squared dx, what does that integral right there become in terms of my substitution that I made? So what does dx dx become? What does this become? Negative 1 over 2 pi squared du, right? And I can pull all that out. So negative 1 over 2 pi squared, right? Integral du. That's just what the x dx became right there. And then what's still in here? 1 over the square root of u, right? 1 over root u, which is really u to the negative 1/2. And I put it as u to the negative 1/2 because I'm going to take the antiderivative. If you haven't done your homework from last class, you're probably sitting here with your head spinning. And even if you did your homework from last class, it might still be spinning, all right? don't know. I wish we could do Cal 2 over an entire year. It would be much better, but could really take our time. But I think that's part of the challenge of the class is can you keep this pace? What's the antiderivative of that? 2u to the 1/2. And then plus c, but I'm not even going to do plus c because we're going to do a plus c when we're done with our answer. These twos cancel. And what was u?
1 minus pi squared.
So square root of 1 minus pi squared x squared. There we go. So remember where we were. We were right here, right? And we said, hey, can we do that? And it was like, yeah, we can do a substitution. Basic substitution works. Here's what happens when we do the basic substitution. That antiderivative becomes this. So that is now the answer to that part. But what's still in front of it? A negative pi is still in front of it. So we got to write our final answer now. Okay, that's done with my scratch work. So this now becomes equal to x arc sine of pi x, then what? Minus pi times that. So what happens when I take negative pi and multiply it times that? Plus, just 1 over pi now, right? Because one of those pi's cancel. And then I've got square root of 1 minus pi squared x squared. Bam. Plus c, thank you, plus c. There it is. So that was an integration by parts. Started out with Luis. He chose u to be the arc sine of pi x because that was really the only choice he had. We worked through it. We got this worked out, cranked out, and looked at that, said, oh crap, that looks terrible, but then realized it's just a basic substitution. Worked the basic substitution out, plugged it back in, made sure we accounted for all the signs were there. Now, how could we check this answer? We could take its derivative. And what should we get when we take the derivative of this? Arc sine of pi x. Right? That's what we should get. So I do it fast, okay? Here we go, real fast. Product rule. Product rule, derivative first one? 1. Then times second one. So arc sine of pi x. Plus derivative of this. What's derivative of that? 1 over square root of 1 minus pi squared x squared, but then I'll have a pi that pops out, so that's going to be right there, times the first one, which is x, so I'm just put that x on top like that. Okay, plus 1 over pi, derivative of this. Derivative square root of something is 1 over 2 times the square root of what was in there, times the derivative of what's inside, which was negative pi squared, negative 2 pi squared x. Yes? That pi cancels with that pi, and this 2 and this 2 cancel. And so at the end of this, this is just minus pi x over square root of 1 minus pi squared x squared. But that term cancels with that term, and you got that. I know I went super fast, but it works, okay? It works. So now can you appreciate that, like when you're in Cal 1, when we take derivatives, very clean, like procedurally, it's clean. The derivative of that, clean. The antiderivative of a very simple looking expression can be a very complicated looking expression. Because when you take the derivative of it, there's a lot of things that have to work out perfectly to get just this thing to stay here. So how do we do it? Well, we have a couple of things. Integration by parts. We got U substitution. We've got power rule. What don't we have yet? Trig sub, trigonometric substitution, trig integrals, partial fraction decomposition. So we're really got just a few more methods. How do y'all feel?
Mark. I have a question about that pi squared x squared. Isn't that a product rule?
When you took the derivative,
Yes.
it's a constant. Pi is a constant. So it's the same as like if you had like 10x squared, how would you take derivative of that?
Oh,
You just bring down the 2 and you'd say 20, right? So the pi squared is as good as a 10.
very good.
We had a pi squared though. So I
Yes.
guess it would just be like, it would be like 100x squared in that case.
Yeah, yeah. Pi squared is still a number,
Yeah,
right? The fact that it's raised to a power doesn't change the fact that it's still a constant.
very good, thank you.
Okay. All right. I'm trying to weigh the benefits of whether or not I should do the next one or not. I mean, I do it every other semester. I do this problem, so I don't want to sell you all short. So somebody who has the book, does anyone have the book that still has the formulas in the back? Someone hasn't stolen them out of the book? You have? Okay, so there's a formula that's in your book that is not on the sheets that you can bring to class, okay? In fact, I allowed you, the book has a list of all these antiderivatives for all these different functions, and I gave you, you can only have reference page 6, so it stops at formula 29. But in fact, the rest of the formulas, there's formulas 46, 91, 94. There are actually 120 formulas for integrals in here. So if you're integrand, if this thing looks a certain way, there's formulas for it, 120 of them. And I've seen books this thick full of integral formulas. All right, I've seen them just full of formulas for integrals. But it is 2002, right? 2020, almost. And what do we have? The almighty computer, right? So, you know, when it comes to things like this, in the real world, okay, in the real world, I promise you that if you have to do an integral in your job, you're going to go to a computer, okay? You're going to. 15 years ago, maybe, that wouldn't be the case, but now, definitely you would go to a computer, which makes you sit here and go, well, why are we doing this, really? Right? Kind of. But there's something about this that is going to separate the people who can and the people who can't. Does that make sense? Like this is a weeding out procedure. Can you get through integration techniques? Because it's a higher level of thinking. Can you all see that? It is? Can you all see it? The difference from calculus already? Okay. Now I'm saying everyone in here can do this. It's just, it's effort, it's motivation, it's willing to get it wrong, try again, get it wrong, try again. And I think even though in the real world you might not use that skill, you may not actually need to do integration, the people who can do this are going to be, I think, better engineers and computer scientists than those who can't do this. That's the way I feel about it. I mean, like, I want someone who can think at this level building a bridge, you know, not someone who has trouble with this sort of thing. Am I making sense? I'm not trying to talk down to you. It's not an insult. It's just I'm trying to get you to see value in what we're doing here. You know, it's like passing Cal 2 is a notch on your belt. It's a big one, and it should mean something. And so, yeah, all right. I'm yapping. So in the formulas, there's one on here, what was it, like formula 70 something, says this. It says that, there it is, 73. It says antiderivative of sine to the n of u, I'm going to do x instead, dx, is equal to, wow, look at this crazy formula, negative 1 over n sine to the n minus 1 of x cosine of x plus n minus 1 over n integral sine to the n minus 2 d sine n minus 2x dx. All right, let's make sure I've copied this down right. Okay, there it is. This is a formula for if you ever wanted to do something like the antiderivative of sine to the 8th power of x dx. Like let's say we wanted to do that. This formula says that I can use this formula, can't I? So this formula says the answer will be negative 1 over 8 sine to the 7th x cosine x, okay, plus 7/8 integral of sine to the 6th of x dx. Right? That's what that formula says. And then how do we deal with this? We use the formula again. So this right here, you would have to apply that formula to that piece again. And in that new formula, what would you get at the very end, the new little integral at the end? Sine to the 4th, right? And then you'd have to use the formula again, and then again, until you get it all the way down. Make sense? So if you change that with an 80, like in theory, we could do that, right? You would have to, first one through would get it down to a 78, then a 76, then a 74. Right? These are called reduction formulas. And where do you think these reduction formulas came from? Where do you think that came from? Someone derived it, right? It was definitely not found like in some tablet that had all the math formulas in it, right? It's like, holy wow, look at all this. No. You had to come up with these, right? So that's what we're going to do. We're going to generate this formula. All right? It looks worse than it is. It looks worse than it is. What do you think they used to create this formula? Integration by parts. Do you all see that we kind of have like an ultraviolet minus voodoo? Kind of? It is kind of like an ultraviolet minus integral voodoo. Now we don't have minuses, but it's okay. So let's just take a stab at this. What do you think we would use for our U and our D? This one's so tricky, but it's a formula. And trust me, somebody else suffered for this, okay? So I think we might be able to get it if we can realize what that is. That's supposed to be U times V, right? In our integration by parts. That's supposed to be U times V. So what do you think maybe V is? Cosine? Right? Like imagine that this is cosine x. Then this right here would be V, right? So that would mean that dV would have to be what? Sine x. And what would that force U to be? Oh, sorry, sine x dx. What would U have to be then? Yeah, sine to the n minus 1. See, how many sines do we have here? We have n of them, right? If I peel one sine off, I'd have sine to the n minus 1 of these. So in other words, what I'm telling you is that whoever came up with this formula first realized that what they could do is split this up into the sine to the n minus 1 of x times sine of x. And they did that so that they could give themselves a u and a v, sorry, a u and a dv, right? They created that first. And that creates this table. Now we integrate sine. Now does this work here? I'm off by sine, aren't I? I need to make that minus. So that's that. And then this right here, what's the derivative of sine?
N minus 1 sine.
Yeah, so how would we take derivative? And let me need more room here. Du is power comes out, right? N minus 1 times sine to the what? N minus 2, right? Power comes down by 1. So imagine that was like sine to the 7th x, right? Derivative would be 7, sine to the 6x times cosine of x dx. Okay, I can just tell by looking, and I've got 5 minutes left, and I want to talk a little bit more about the exam. I think I should just abandon ship on this right now. Yeah. Because of the amount of work it's going to take to actually finish this, I'm not going to have enough time. But that's the setup for it. I mean, this is it. You just do ultraviolet, right? Here's ultraviolet, and that's that. And then you do your voodoo. Then you have to use some trig identities, and then eventually you get that integral over there to show up again over here, and then you add it to both sides. And like I said, somebody else suffered a very long time to get that formula, but they got it. And all it is just the application of integration by parts. So the exam, I have it right here. Unfortunately, you don't get to see it. Can't be found. Okay, so it's on that SD card that's in that camera. And in order for me to get it here so I can talk about it, I have to stop the camera. So what would you prefer I do? Talk about it on camera or take it out and look at it and talk about it off camera?
I can video it.
Okay, all right. So I'm going to turn it off. I don't know. I don't need the video. This is for you, not me.